Grind 75, C++, we're doing word break today. Given a string S and a dictionary of strings word dict, return true if the string can be segmented into a space-separated sequence of one or more dictionary words. Note that the same word in the dictionary may be used multiple times in the segmentation. Now they give a couple of examples. So for example, if you got LeetCode and you have a dictionary of leet and code, you want to return true. Seems pretty obvious. And if you have apple, pen, apple, say that 5 times fast, and your dictionary is apple and pen, you also want to return true. You're reusing apple, but that's fine. And then they give a negative example down there that should be false. So I'm going to talk first about kind of a red herring approach. So it's words, it's string, it's potentially prefix matching. You'd think that using a try would make sense here. So in that case, you would instantiate a try using this word dict in those entries, and then maybe use a greedy algorithm to iterate through S, and whenever you find a potential word break, when you come, for each character in S, you step through word dict, and every time you hit the end of a word in word dict, it will be marked, you'll know. Then you restart from S, and you keep going until you have like and if you end in the middle of a word or something, or if there's a character that's just like not a valid next prefix in what you're searching in word dict, then you'd return false. Something like that. That has a couple of problems. First of all, it's a greedy algorithm which has its problems. The main problem being, what if you accidentally mark a word as successful? So you've got two potential words. You've got, say, apple and the word A, just the letter A. I should write these down. You have both of these words in your word dictionary. Well, you don't want to prematurely mark a section of the string, of a prefix of it as breakable, because maybe you need to consume these following characters in order to get to some valid next thing. So if your word is like apple, pen, you don't want to break it at A, because pool is not a word, and then you'd end up returning false. So how do you account for that? Let me see. Is there anything else I wanted to mention? No, I'll go into the actual solution. So it's dynamic programming, and it's done in such a way that it's still quadratic-ish. Quadratic-ish. What you end up doing is you create your dynamic programming table is an array of booleans, and then you'd step through the characters in S, and you'd look back at prefix, the X number of characters for each word in the word dictionary. You look at the preceding number of characters in S, check the length, and you compare that to the word. And you'd end up doing this for every potential character in S. You end up looping through every word in the word dict, so you end up with O of, let's say, NM time, where N is the number of characters, is the number, and M is the number of characters in the word dictionary. And why is it the number of characters in the word dictionary and not the number of words in the word dictionary? Well, you're comparing every word in this dictionary to some prefix in S. And as you loop through this word dictionary, it's got some total length. If you were to concatenate all of the entries together, you'd have some total length. You're looping through all the words, but you're going to go through that total length once no matter what. So if it's got many, many words that are short, you'd end up doing the same number of like comparison keys, or no, comparison strings, string comparisons. You end up comparing, say, a bunch of short words against a short prefix. Well, comparing two strings is linear time on the lengths, but if it's many, many short versus a few longer ones, you end up with the same like total amount of work, so it ends up kind of balancing out. So it's number of characters. And that's where this is the quadratic runtime. And then it's going to be O of n space for the dynamic programming table. Yeah, I'm going to go ahead and start writing out some stuff. So first I need to declare the table. It's an array of Booleans. We're returning a Boolean. The entries of our table are going to be Booleans. It's worth mentioning that how silly it is to do an array of Booleans when really you should be doing an array of bits. Some byte type, maybe character with some bits in it. I'm going to still do the array of Booleans in this example, and that's something that you should definitely ask your interviewer about as you're writing it down. See if they have a preference one way or another, but just show that you're cognizant of how silly and in production, you'd probably want to do bit bashing and do like some array of bytes, or I don't know. You need something that's for sure at least as long as the string s, and that's where the tricky part comes in. That's why I'm gonna just do a vector, because how do you know that you don't have some super long string? If it's more than 64 characters, you're gonna have to use some non-standard type. Maybe a byte array. In that case, you have this like nested array, and you end up like doubly indexing, and I don't know. I'm just not going to deal with it. So vector of Booleans. Ooh, I cringe writing it. And I'm going to call it T for table. And it's going to have a size of the size of S, so S dot size plus 1. And the reason for that is we need a base case. And so there's one extra entry for their base case. 1, and then it's going to be initialized to false. And our base case is going to be true. The base case being if the string s is empty, then it's going to be true. But we have this condition where our input is always going to be at least length 1 anyway, so that's fine. The base case isn't going to throw off our output. All right, what do we do next? There's going to be a main for loop. This is going to be, it's a linear, I don't know if linear time's not the right word. The outer loop is linear on the input size, but then inside each loop is going to be another linear time string comparison. So it's technically linear, so you just need the one-dimensional table. For int I equals starting at 0. And I'm going to declare another like temporary variable. I'm going to call it I start. I'm not going to initialize it yet, but that's going to hold. It's just like it makes the display a little cleaner. It's going to hold the starting index of the substring we're going to compare against. I is less than the size of S and we have to do one extra iteration. So it's the size of S plus 1. The reason for that being we're shifting over by 1. But we still need to consider the base case. I don't know. We probably could just start from I equals 1 to the size. I don't know if we need to start at 0 or 1 actually. I got to think about that. But we're going one extra iteration and then increment I. So what do we do inside here? First, let's add our return statement at the very end. Return t.back, the very last element of our array. If it's true, then we have the whole word is breakable. I should probably start. Let's take a step back. Dynamic programming breaks the approach into several smaller subproblems. So we're starting with this base case of 0. If you got an input, so if your input is LeetCode, and your word bank is LeetCode, you're starting with some prefixes. So first it's the empty string. And then on the next loop, it's going to be, is this breakable into by the word bank? And next one is this breakable into the word bank? And you just keep progressively adding an additional character until you've got your whole output. So this is your second to last iteration. Is this breakable into the word bank? And then is this one breakable? That's the whole thing. So that's the gist of dynamic programming. So we have our main loop, and we need to do our check. So if, what do we check? We want to see if the preceding substring, so we've got okay, we need a loop for each word in word dict. Okay. For each word in word dict. If we need our starting index. So if we're comparing the substring, we've got the size of this word. So I start is the size of it's our current index minus the size of the word. And we want, if that's less than 0, if it's negative, then that's our comparison word is bigger than our existing prefix. So that's fine. We're going to skip it. So if I start is greater than or equal to 0, and what do we need to do? So the key here is, say we've got, okay, our array table, we're going to be looping through. So T is going to be, we're going to initialize it as 1. So LEETC, and then 1 extra. We're going to be looping through. We want to compare. So we've got these words. By the time we get to the end of, we're actually comparing this leet value. So I start if that's at least big enough for the prefix. You'd think it would be here, but actually our letters in S correspond to 1 over in the table. So it really, the first 4 characters of our input word, input string, that corresponds to here. So we want to check if we've gotten to this point and the word so far is breakable into our word bank things, then we're going to check that here. So we need to use this is the part where we reuse our partial input in the table. And T I start. And then we do the actual comparison. So the way this example is going to work is we would look through here. So LEET, and we have this. I start is going to be 0 for once, or index 0. So that means it's true. And then we continue on to our actual word check. Well, what if it's not true? If this, if that were false, that prefix before, well, that means that our input string, if we were to take the part before this final word, so it means that this current word is in the word bank is too short. It's too short. We need a longer one that looks farther back because there are some letters that were not consumed and put into an actual final word. That's what that means. So I start and word equals what? The way that you can do substrings in C++, it's the syntax is the substring command. So you have s.substr This is how you do string slicing. And that's going to be, so I start. The syntax is the starting index and the length. So the length is the size of our word. So word dot size. The substring immediately preceding the substring out of the input word, the size of the word bank word. If those are the same, then we've got a match and we can declare this prefix part true. And if this part is false, again, that means that the current word is too short. We need a longer one. So hopefully we'll hit a longer one on the next iteration of this inner for loop. And if we don't, that means it's not possible and we'll end up returning false overall. So T of I is true. And I think that's it. That's pretty much the whole thing. So I'll just do this one example of LeetCode because I don't think these other examples really add a whole lot to it. All right, so we initialize. This is our initial table value. And then we start going through our input. So I equals 0. Could probably start with I equals 1, to be honest, because I don't think it really matters. I don't know. It doesn't affect things much either way. So I equals 0, 0, and then we go through the words in the word bank. Those are always going to be negative. I equals 1. We check leet and code. Those are both size 4, so that's negative. So we're gonna have these negative indices, and then we're gonna fail this check up until here. Index 4, 0, 1, 2, 3, 4. At this index, this check is gonna pass. And then we're going to look back at I start, which is 4 before, so the size of leet. We're first looking at leet, so L-E-E-T, that is true. That means we can now compare the substring of our input word, starting one before, so starting at index 0, I start as 0. We're looking at our input, L-E-E-T, because we're looking at size 4. That is the size of this here. That is a match. So we're going to go ahead and mark this as true and keep going. So this negative index check is going to pass every time from now on. And then this is going to be our main constraint. So now we're looking at LeetCode. Let's go ahead and do this. So LeetCode, size 5. Our I start is, but we're looking back 4, but these are both size 4. So that's false, that's false, that's false. That's true. So we're not going to pass this check here until we're looking at the end, pretty much. Yeah, so we go from here, and we have to shift 4 over. 1, 2, 3, 4. Now we're looking at this. So first we're looking at the word leet. That is the first word in our bank. We've passed this, we passed this. Now we're comparing this. We've got this prefix. So I start, which is 4 prior to our current index. And our current index is the length of s minus 1, basically. So it's the very end. So we're looking at this. That's not equal to leet. So this check fails. Continue to the next word, and then this time it's going to be comparing this bad boy. Wait, no, it's still comparing code. So now it's comparing code to code. That is going to pass. We're going to mark it as true. And when we return the very last element in our table, that's the end of the string. We break out, return, and that's it. I think that pretty much covers everything. Yeah, it's pretty straightforward. It's a kind of a classical dynamic programming approach. The real tricky bit, I think, is noticing that it's dynamic programming and not like a greedy try search, like try TRIE. And that's it. Let's go ahead and give it a run for syntax. Accepted. Cool, cool, cool. And submit. All right, and we're gonna mark it off, and you folks have a beautiful evening.